Now we're going to recap our lectures on the sampling distribution. We're going to talk about what the sampling distribution means, and we're going to demonstrate again how we answer questions on the sampling distribution. So this is really a review of material that's already been presented. So let's consider the population for the number of text messages sent per month for all Americans. The population means all. So our population that we're investigating here is all Americans. And we're told that it's normally distributed. If you're told that a population is normally distributed, you could model that population using the bell curve. So the bell curve here represents 100% of our population, and since our population is all Americans, this bell curve represents 100% of Americans. On the horizontal axis, we'll label our variable, which is the number of text messages sent per month. So that's our variable. And if we consider the way the horizontal axis works for the bell curve, on the left side we have small numbers, and on the right side we have large numbers. Those small numbers on the left represent the number of text messages sent per month, and if they're small, it means that that represents people in the population who sent very few texts per month. So right here we're looking at people that send very few texts per month. And on the other side, we're looking at people who send many texts per month, because again, the horizontal axis goes from small to large, small numbers to large numbers. So here we have very few texts per month, and here we have many texts per month. The height of the bell curve represents frequency. So at the highest point, we have the highest frequency, and at the lowest points, we have the lowest frequencies. And if you look at people who send very few texts per month, you're looking at a very low frequency of people. Not many people send very few texts per month. And if we look at many texts per month and we look at the frequency associated with many texts per month, we see that very few people, because the frequency is not high, the frequency is low, very few people send many texts per month. Now, we don't really have a lot of information here. We don't know what numerically many texts means or what numerically very few texts means. At this point, we're just looking at the shape of the bell curve and what either side of the bell curve means. In the very center, we have the average number of texts sent per month, and that population average is represented by mu. And in a bell curve, in a normally distributed bell curve that is symmetrical, the average is always in the center and it's always the point of highest frequency. This is material that was covered in Chapter 7. And we need to know this, we need to understand this material before we can explore the idea of a sampling distribution. Right now we're just looking at a regular population. Now let's take a look at what happens from that population of all Americans if we sample. So let's take 100 random people from that population. And let's suppose from that 100 people that have been sampled, we take the mean. And that's going to give us a number that's represented symbolically by x bar, the sample mean. So here's our population. From our population, we randomly select people, members of the population, and they become a sample. We find the mean of this sample here, and that is represented by x bar. Okay, so let's go back to the population and randomly sample another 100 people from the same population. That's going to give us another sample mean, another x bar. So we'll take another 100, we get another sample, we get another value for x bar. And we can do it again. We can keep sampling groups of 100 people from the original population. So if we keep randomly taking groups of 100 from our population, we keep getting samples of size 100 and we keep getting different values for the sample mean, x bar. So this sample has an x bar, this sample has an x bar, this sample has an x bar, and I think I have one more. Yep, this sample has an x bar, and we can keep doing this until we have many, many x bars. We can do it for all possible combinations of 100 people taken from the population. That's a lot of samples. Now, all of these samples that we've accumulated have their own sample mean, x bar. So if we consider all the sample means, all the x bars that are generated from each of those samples, we have a collection, and that collection is called the sampling distribution of sample means. Sometimes we just call it the sampling distribution of means. Now, the central limit theorem was a theorem that told us if we had original population, or if we had an original population that was normally distributed, which means it was based on the bell curve, or the sample size that we used to get our sample means is more than 30, then the sampling distribution of means is also normally distributed. In other words, this collection of all sample means, which is going to be a lot of sample means, the collection is also normally distributed. It is also based on the bell curve. So now we have a new bell curve that represents something else. It represents a collection of all possible sample means. So if it's normally distributed, it is based on the bell curve. But the horizontal axis at this point does not contain the same variable, or shouldn't be labeled with the same variable, and doesn't contain the same numbers as the previous bell curve, which was based on the population. This bell curve represents all possible sample means for the number of texts sent per month for samples of size 100. So these values on the horizontal axis represent sample means. So that's why the horizontal axis is labeled sample means for the number of text messages sent per month. Again, the height of the bell curve represents frequency. That stays the same. On the far left, you're looking at sample means with low values. So this x bar over here is a sample mean with a small value, a small sample mean. And then as we progress along the horizontal axis, our sample mean on the right is a large sample mean, because numbers get larger as we move towards the right on the horizontal axis. And then right in the center, we have a sample mean that's numerically in the middle, and that is equal to mu. That is always equal to the population mean. That's something that we saw at the beginning of the last lecture on sampling distributions. This sample mean in the center is always equal to the mean of the population mu. Because the sampling distribution of means is normally distributed, bell curve, we can answer probability questions, because anything that's based on the normal distribution can be answered with, or can have probability questions answered with normal CDF. Because area equals probability. If we can figure out the area under the bell curve using normal CDF, we can answer a probability question. To find the area under the curve, we need to know the mean and standard deviation of the sampling distribution, because if you remember, using normal CDF, the first two entries are the lower and upper limits, but the second two entries, or the third and the fourth, are the mean and the standard error. So we need to know those two things. An important relationship is that the mean of the sampling distribution is the same as the mean of the population. I just mentioned that. The mean in the center, x bar in the center, is the same as mu. But we use a different notation. We don't use mu. We use mu sub x bar when we are referring to the mean of a sampling distribution. Now that mu sub x bar can be interpreted as the mean of all sample means. So the mu is the mean, and the subscript x bar tells us that we're talking about sample means. So the mean of all the sample means. And then we have notation for the standard deviation of the sampling distribution of means, and that's called the standard error for short. And this is how we denote it. Sigma subscript x bar, which represents the standard deviation of all the sample means, because remember our collection for this distribution is a collection of sample means. So this is the mean of all the sample means, and this is the standard deviation of all those sample means. And the formula that we use to figure out the standard deviation of all the sample means is sigma, the standard deviation of the population, divided by the square root of m. So a lot of times you're going to see textbooks, and also in my lectures, I will refer to this sigma x bar as the standard error. The sampling distribution of means is a normal distribution, and the horizontal axis represents all possible sample means represented by x bar. So over here we have small values of x bar, and over here we have large values of x bar. In the center, we have the mean of all sample means, which is the same numerically as the mean of the population. And then we'll usually also label the standard error right beneath the mean of all the sample means.